Hello everyone. Today we are going to analyze this propped cantilever beam. In this beam, we have uniformly varying load. It varies from 0 in the point B to W in the point A. In this beam, the upward deflection due to the vertical reaction RB will be equal to the downward deflection due to UVL. So area 1 x1 bar upon EI is equal to area 2 x bar 2 upon EI. We know that in this beam EI is constant, so we can eliminate EI so that we will get this. Now from the point B and about the point A, we are going to find the bending moment values. We are going to find the moments separately, first due to RB and then due to the UVL. In this case, we have to follow left-hand side rule. Clockwise will be negative and anti-clockwise will be positive. RB is acting in the anti-clockwise direction so that it will be positive and the distance is L. RB into L, we will get RBL. The diagram will be in the shape of a triangle. Now let us take the UVL. In the case of UVL, to get the moment, we have to multiply the area with the centroid distance. We know that it is a triangle. We know the area formula of a triangle, half into BH. Here the breadth is L and the height is W. So half into L into W. We are calculating the moment about the point A. So about the point A, the centroid distance is 1 upon 3 into breadth. Here the breadth is L. So 1 upon 3 into L. The UVL is acting in the clockwise direction so that the moment will be negative. For the moment due to UVL, we will get minus WL square upon 6. The diagram will be in the shape of parabola. Now let us find area 1 x1 bar. We know that it is a triangle. We know the area formula of a triangle, half into BH. Here the breadth is L and the height is RBL. So the area is half into L into RBL. Let us find x1 bar. We have to find the centroid distance about the right side. That is 2 upon 3 into B. Here the breadth is L, so 2 upon 3 into L. Now let us find area 2x2 bar. This is a third degree parabola. The area formula of a third degree parabola is 1 upon 4 into BH. Here the breadth is L and the height is WL square upon 6. So this is the area. Let us find x bar 2. The centroid distance towards the right is 4 upon 5 into B. Here the breadth is L. So 4 upon 5 into L. Now let us equate area 1 x1 bar and area 2 x2 bar. We can eliminate these two and these two. L into L into L, we will get L cube. We can eliminate this 4 and this 4. 6 into 5, we will get 30. L into L square into L, we will get L power 4. We can take L cube upon 3 on the other side. It will come inversely. We can eliminate L cube and power 4. And we can eliminate 3. Here it will be 10. So for RB, we will get WL upon 10. Now let us apply the rule sigma V is equal to 0 and find RA and RB are acting upwards. So both of them are positive. The uniformly varying load is acting downwards, so it will be negative. Here the total load is the area. We know the area formula of a triangle, half into BH. Here the breadth is L and the height is W. So half into L into W. In this way we can find RA, which is 2WL upon 5. Now let us take a moment about the point A and find MA. RB is acting in the anticlockwise direction so that it will be positive and the distance is L. The UVL is acting in the clockwise direction so that it will be negative. To find the moment, we have to multiply the area with the centroid distance. About the point A, the centroid distance is 1 upon 3 into B. Here the breadth is L, so 1 upon 3 into L. MA will be acting in the anticlockwise direction so that it will be positive. Finally, for MA, we will get WL square upon 15. Now using the right hand side rule, we can find the shear force values in the point A, and then using the left hand side rule, we can find the shear force values in the point B. Here you can see the shear force diagram. In this point, the shear force becomes 0. In this point, there will be maximum positive bending moment. In this point, let us make a section and to find the distance. You can see that I have made a section in that point at a distance of x from the point B. In this section, we have to find this height. For the distance of L, the height is W, but we need the height at the distance of x. So we have to multiply with the x so that the height is Wx upon L. Now let us find the shear force in this section from the point B. We know that in this section the shear force is 0. We have to follow left hand side rule. Upwards will be negative and downwards will be positive. RB is acting upwards so that it will be negative. UVL is acting downwards so that it will be positive. For the UVL, the shear force is the area. For this triangle, the area is half into x into Wx upon L. We can take this term on the right side, so it will come as positive. We can eliminate W and this W. We can eliminate this 2, so that here it will be 5. X into x, it will be x square. We can take L on the other side. L into L, we will get L square. Then we can take root on both of the sides. In this way we can find x, which is L upon root 5. Instead of x, we can apply L upon root 5. In this expression, instead of x, we can apply L upon root 5. We can eliminate L and L. So for the height, we will get the expression as W upon root 5. Now let us make the expression for maximum positive bending moment. RB is acting in the anticlockwise direction so that it will be positive, and the distance is L upon root 5. UVL is acting in the clockwise direction so that it will be negative. For the UVL, we have to multiply the area with the centroid distance. This is the area and this is the centroid distance. For the maximum positive bending moment, we will get WL square upon 15 root 5. We know that in the point B, the bending moment is 0. Now using right hand side rule, let us find the bending moment in the point A. In the point A, we have MA, which is acting in the anticlockwise direction so that it will be negative. Here you can see the bending moment diagram. The diagram will be in the shape of cubic parabola. In this point, the bending moment becomes 0. We know that this point is the point of contraflexure. We can make a section in this point and make an expression for the distance. You can see that I have made a section in that point at a distance of x from the point B. Using the left hand side rule, we can find the movement and we know that it is 0. For the distance of L, the height is W, but we need the height at the distance of x, so that we have to multiply with the x. We will get the height as Wx upon L. RB is acting in the anticlockwise direction so that it will be positive and the distance is x. UVL is acting in the clockwise direction so that it will be negative. We know that for the UVL, we have to multiply the area with the centroid distance. From these two terms, we can take Wx outside, and then on the other side, 0 upon Wx, it will be 0. X into x, it will be x square. 2 into L into 3, we will get 6L. We can take this term on the other side, so it will come as positive. Then we can take 6L on the other side. 6L into L, it will be 6L square. Then we can take root on both of the sides. For x, we will get L upon 5 into root 15. Let us apply that. Now we are going to make the expressions for the slope and deflection. In this beam, we have to make a section. I have made a section randomly at a distance of x from the point B. In this section, we have to find the moment. Using left hand side rule, we can find the moment. We have already seen how to do that. Let us equate the moment with EI d square y upon dx square. Let us integrate this term on both of the sides. Using this formula, we can integrate. When we integrate x, it will be x square upon 2. When we integrate x cube, it will be x power 4 upon 4. C1 is the constant. 10 into 2, it will be 20. 6 into 4, it will be 24. Let us integrate this term one more time. When we integrate x square, it will be x cube upon 3. When we integrate x power 4, it will be x power 5 upon 5. When we integrate c1, it will be c1x. c2 is the new constant. 20 into 3, it will be 60. 24 into 5, it will be 120. We know that in the point A, there is a fixed support. In the fixed support, there will be no slope. So when x is L, the slope dy upon dx will be 0. In this equation, let us apply both of them. So that for C1, we will get minus WL cube upon 120. Also, we know that in the point P, there is a vertical support. If there is a vertical support, there will be no deflection. So when x is 0, the deflection y will be 0. In this equation, let us apply x is equal to 0 and y is equal to 0. In this way, we can get a C2, which is 0. In these two equations, let us apply the values of C1 and C2 so that we will get these two equations. This is the slope equation. Let us keep this equation as number 1, and this is the deflection equation. Let us keep this equation as number 2. Using these two equations, we can find the slope and deflection at any point of the beam. Now let us find the slope in the property end. For that, in the slope equation, instead of x, we have to apply 0. When we do that, we will have the slope in the point B, which is equal to minus WL cube upon 120 EI. Now let us find the slope in the center. For that, instead of x, we have to apply L by 2. When we do that, we will get the slope in the center as WL cube upon 640 EI. Now let us find the deflection in the center. For that, in the deflection equation, instead of x, we have to apply L by 2. By doing so, we will get the deflection in the center as minus 3 WL power 4 upon 1280 EI. For the deflection, we have got a negative value. That means the deflection is downwards. Now we are going to find the location where the maximum deflection occurs. When there is maximum deflection, the slope will be equal to 0. Let us take the slope equation and equate that to 0. From these three terms, we can take W upon 4 outside and then take it on the other side. 0 into 4 by W, we will get 0. We can take this term on the other side, so it will come as positive. For these two terms, we can take LCM. We can eliminate this 30 and this 30. we can take L on the other side. L into L cube, it will be L power 4. Then we can take these two terms on the other side. They will come with a change of signs. Let us keep x is equal to KL. So instead of x, we can apply KL. From this term, we can take L power 4 outside and we can take on the other side 0 upon L power 4, it will be 0. Then we can take a calculator and solve this equation so that we will get K. We know that x is KL, so x will be L upon root 5. Now in the deflection equation, instead of x, let us apply L upon root 5. After the simplification, we will get the maximum deflection, which is equal to minus 2 WL power 4 upon 375 root 5 EI. Now we are going to end this session. Thank you for watching this video.